I'm Michael. Today talking will be TJ. Uh, Many of you have already seen him, so I don't really need to give him an introduction, ideally. He's a very smart man who's worked very hard on CompuCell and TissueForge, which we'll be going over today. So TJ, take over.
That's quite the introduction. Thanks, Michael. Yeah, for those of you who have not had the pleasure of meeting yet, I'm TJ Sego, assistant professor of medicine, University of Florida. And as I said yesterday, I've been working on CompuCell since around 2019. And the breakout session today that we'll be doing has almost nothing to do with CompuCell at all. But instead is a new project that has emerged. This software project was started in James Glazier's lab, and this is a project that I took on a few years ago, and we've been growing this new package to do new things. Some of it's motivated by limitations, like historical limitations with CompuCell. And so there is some relevance there in the sense that perhaps you've already started to find things that maybe you would like to do in your own projects that aren't particularly obvious in CompuCell. Maybe some of those issues are mitigated in this package that we're going to do a very, very high level overview of today over the next hour or so. And that package is called TissueForge. We have a smaller crowd, so I think we can try to keep it as interactive as possible in terms of just addressing questions and commentary in real time. I'll say that this is jam-packed with all sorts of stuff for us to do potentially, depending on what time permits. So if there are really involved discussion topics, maybe we can save those for after the breakout session. My email is included in a couple of locations that I can add it to the chat as well. You're welcome to connect with me individually outside of the workshop for anything that might be of interest to you on this topic. So today we will do a very brief overview of what is TissueForge, what can you do with it, what's represented in a TissueForge simulation, and to the best of our ability, depending on how much time we have, we will get into some hands-on interactive model and simulation building. We'll do something similar to what we did together yesterday on the Python API, where we will essentially code and learn simultaneously, working on the same thing together. I'll say that it is not necessary for you to complete the exercise today to learn from the content that has been planned. You're encouraged to do so, and I welcome you to. But of course, some of these things are, easier for some people than others to just jump right into. So if you at all feel like maybe it's just better to sit back and, sort of take the information in and just watch, that's no problem at all. These slides are pretty extensive in terms of being able to complete the exercise that's planned from beginning to end, regardless of whether we actually get to do all of it together. The slides will be shared and they'll be available in the shared resources. So whether you wait to do this on your own time, or if we just don't get to everything planned, no problem. You can grab the slides and do all of this all on your own. I will say, actually, before we dive in, for those of you who do plan to code along, I'll say that there we'll have a bit of installation to get TissueForge onto your computer. And you can get TissueForge through Conda. So if you do plan to do some coding along with me and you don't have Conda, I'd say now is a good time to go ahead and start the process of getting Conda onto your computer. We'll use mini Conda. I have some instructions a little bit further that are prepared to do a walkthrough for anyone who's not clear on how to do that, but I'll just say for now, if you want to get a head start on getting set up, if you don't have mini Conda installed, go ahead and install that, and that'll get you one step ahead once we actually get to doing some coding. Also, before we get started, here is a dump of lots of information that's available. I will put all these links in the chat. for your reference, so you're not scrambling to type these things out or take pictures with your phone. So there is a new paper out on TissueForge that surveys the highs and lows of the theory, the numerical details, benchmarking, applications, all sorts of things in this paper from last year in PLOS Computational Biology. TissueForge is open source, and the repository can be found at the second link that I put in the chat that you see here. This is a great way to communicate with the people who develop TissueForge, to report bugs, to request features, just to find lots of examples. There are Jupyter Notebooks and Python scripts available. And then there's a really extensive set, I would say, of documentation, both walkthroughs and a survey of, say, features and philosophy of the project at this first link for documentations. And then there is, I'd say, mostly complete API documentation for all supported languages. We'll be working in Python today. So of interest to the exercises today, the API documentation for nearly all Python support is available at this last link. If you do find things in those API docs that are incomplete or incorrect, an issue is welcome on the GitHub repository to let us know, what ways we can improve these documentation resources. Okay, now we can actually get into the fun stuff. So TissueForge is a particle-based modeling and simulation environment, and it's explicitly within the scope of the TissueForge philosophy to support modeling and simulation all the way from the molecular scale all the way up to multicellular tissue dynamics. And you can see some examples of this here on the right. So we've got a couple of molecules that are constructed here in TissueForge. These are all simulation results from different examples, molecular level to more of a mesoscale, doing transport at a permeable, deformable cell membrane, all the way up to tissue scale cell sorting with over 1 million cells, which, with regard to CompuCell, simulating a million plus cells in 3D to do cell sorting is quite the task and require quite the computing resources. Whereas with the particle-based methods, a simulation like this you can run on your laptop. Not that big of a deal, maybe a little bit slow. And the computational cost will depend a lot on the details that you include in the model. But in general, particle-based simulation with TissueForge and with comparable packages, it's certainly within scope to do simulation at the scale of millions of particles. So this is an approach that uses coarse-grained molecular dynamics. A lot of the detail that maybe you've become familiar with now in multicellular modeling through CompuCell is neglected in the particle-based methods. So typically in applications for multicellular modeling, explicit cell shape is not considered. Instead, there's a simplified representation of cells where each cell is either represented as a single particle or, say, like a small collection of particles. So in applications like this, you're not particularly interested in the details of individual cell shape, but rather more of the aggregate behavior using a coarse-grained representation of cells. Of course, if you're interested in working at smaller levels like the molecular scale, that's all perfectly within scope, and there are a lot of features to support that level of modeling. There's a lot of flexibility to work at these scales represented and all scales in between. TissueForge provides a lot of built-in physics models, whether in solid mechanics, fluids, or electrodynamics. We'll get a bit of a survey of some of those features with a couple of examples, including our interactive walkthrough that we'll do a little bit later. But generally, it's within scope to support all types of mechanics and even, say, multi-mechanics type modeling, just using this software package. TissueForge uses both event and agent-based modeling approaches. Agent-based modeling approaches are probably familiar to you now, at least at this point in the workshop, with working with CompuCell. So you've developed some models that describe various aspects of a simulation on the basis of individual cells, which is generally referred to as agent-based modeling. TissueForge additionally has a number of features supporting event-based modeling, which is to describe modeling or simulation events that occur at specific times or with some specific regularity throughout a simulation. TissueForge uses a type-centric model specification. We'll see what that means a little bit here shortly. But in general, models here are defined with explicit definitions of types of particles. And so particles, if you think of them as cells or as molecules or as atoms, all of the model spec is defined in terms of particles by type. And to the extent that we've really been able, to support, TissueForge provides a lot of features for supporting custom events. The types of models that you've been developing in CompuCell using steppables, TissueForge provides a similar level of support to be able to inject your models into simulations. And in TissueForge, these points of entry are typically introduced through events. If we can get to it today, we'll do a little bit with events, and you can see what that means. To this same effect, there's a lot of support as well for defining custom potentials and forces to describe the interactions between particles. And then one of the really cool things about TissueForge that it makes it somewhat unique among similar packages is that you also have complete control over the population of particles in a simulation. So as you're executing a simulation, you have the ability at any time to create particles, destroy particles, change the way that they interact all through events. And to that effect, TissueForge also provides a lot of support for interactive modeling and simulation. So there is a couple of different ways that TissueForge can be used. It's certainly straightforward to just run in headless mode, where you define a simulation and then just execute it and review results later. But I think what's more fun is to execute TissueForge interactively. This is just a video of a screen grab that I took while messing with just a very simple simulation with vertex modeling. And you'll notice the browsing around, changing things about this simulation in real time. This is mostly just me aimlessly clicking around, moving the view, and then modifying the simulation with my keyboard as the simulation executes. So to that effect, there are ways to interact with a simulation through keyboard-driven events that you can pre-program into your simulation so that you have interactive control over your simulation through your keyboard. There's a lot of functionality for programmatically modifying and customizing the way that simulations are visualized. You can program up the camera to make something like a movie. You can customize all sorts of details about colors and opacity and things like that. And then there's a good bit of support for GPU acceleration of large-scale simulation. So if you happen to have a GPU handy on your machine, or if you have access to a supercomputer that has a nice array of GPUs, TissueForge is a good package to be able to offload expensive like large-scale simulations onto GPUs, to get those big simulations done before the end of the universe. And a big aspect of TissueForge is openness and accessibility. So TissueForge currently supports a full user-facing API to define models and simulations and control them in the C, C++, and Python programming languages. Again, we'll work in Python today, but it's certainly possible to do everything that we'll survey today, plus more, either in C or in C++, with, of course, a lot of variability in terms of how straightforward it is to accomplish things, and then corresponding, computational performance. It's also possible to execute TissueForge simulations both in Jupyter Notebooks and interactively in an IPython console. So you can actually pull up an IPython console and define and interact with a simulation in real time, excuse me, as it executes. So you can actually inject more code into a simulation as a simulation is executing. And then everything about a TissueForge simulation can be saved to file and reloaded later. So a whole simulation state can be dumped to a JSON file. You can load that JSON later and TissueForge will pick up right where you saved it. You can also even take individual model components and save those to file as human readable JSON as well. So you can say, define a particle type, save it to JSON, send it to Michael and say, hey, Michael, check out my particle type. This is pretty cool. And you can just load it into a simulation and use it exactly in the state that it was when you saved it. We can advance here. I think the recording might be slowing my computer down a little bit.
If you think you need to end it, the cloud one should work. Okay.
There we go. All right, and lastly, on the topic of accessibility, TissueForge is permissibly licensed. You can integrate TissueForge into your software packages if you're building things on top of, say, some particle dynamics modeling and simulation. You're of course welcome to fork the repository, make your modifications, and issue pull requests for features that maybe you developed on your own and think might be useful in the main distribution. There are a lot of features implemented to facilitate these processes at various levels. So as we've already briefly discussed, TissueForge pre-built binaries are available through Conda, but there are also supporting features in the repository to set up a development environment for you. So if you're interested in actually developing your own custom features in the back end of TissueForge, you can find automated scripts to set up the entire build environment for you so that you can skip dealing with dependencies and get straight to coding up your own hacked version of TissueForge. All right, let's very briefly get into what some of the model specification looks like. I'm not going to indulge myself in comparing and contrasting between TissueForge and CompuCell. Hopefully it's somewhat obvious how things are similar and how things are different. Again, we can have some brief discussion of that as time permits, but of course we can also talk outside of the breakout session and the workshop if you're interested in the particularities here. So as I said previously, TissueForge has a particle type-based specification. And I think a really intuitive way to think of this is demonstrated with just the stymine molecule. So in the simulation that defines what you see here, there are 4 types of particles that are defined in this specification. And those types are hydrogen, carbon, nitrogen, and oxygen. It's all of the atoms that are present in this particular molecule. And what you'll notice is that there are multiple hydrogens. You've got a couple of nitrogens and so on and so forth. Each of these particles is a distinct individual particle, but each of them corresponds to a particular type. And when developing a model specification, one defines the types first and then uses those types to create instances of particles of those types. And we'll get into what this looks like in practice, but that's the general way to think of this, regardless of the application, is one first defines types and then creates instances of those types using the type specification. TissueForge also has this interesting sort of meta object, which is called a cluster. Some of this is a little into the weeds and beyond the scope of our discussion for today, but in case you do dive into the documentation and you see this additional concept called a cluster, TissueForge allows you to assign something like a hierarchy of objects within objects, something like constituency. And another obvious example here is a molecule again. So if you find the example that builds this molecule, what you'll find is that each of these particles, there are instances of these particular types, but then you will find that there is a meta object that is a cluster, and that cluster is the molecule. So the molecule itself in the simulation doesn't actually exist, but it is a meta object that owns all of the atoms of which it's built. Now, this has all sorts of interesting implications depending on how you use it. Again, we're going to mostly not go into this level of detail today, but this is an interesting one if you really want to get into some detailed either molecular dynamics modeling or even more detailed multicellular modeling. TissueForge has a couple of different ways that one can do particle-based dynamics. It tends to be especially relevant depending on the application. So Newtonian dynamics, force equals mass times acceleration. This is one of the two types of dynamics that TissueForge can impose on particles by type. And this is what one would typically use for doing like classic molecular dynamics. Whereas very often when doing more of like multicellular modeling, one tends to use over-damped dynamics or Langevin dynamics. A good example is with this cell spheroid simulation. So if you try to do this with Newtonian dynamics, this just doesn't do anything particularly realistic. Whereas over-damped dynamics is something like the continuous analog to the cellular POTS model. So if you're interested in multicellular dynamics, probably this is the type of dynamics that you'd like to use. And again, these types of dynamics can be assigned to individual particle type in a specification. There are all sorts of ways to define how particles interact with each other. The obvious and I think like sort of classic description is the potential. And this is, let's say there's an analog to a POTS-based specification, like how you've been using models in CompuCell. In CompuCell, there's something like a Hamiltonian expression that is used to implement some particular model, say like a volume constraint. In TissueForge, one of the main ways to prescribe interactions between particles is through a potential function that is used to then derive forces on particles. So particles interact through potential-based functions and forces just deciding where they move, how their trajectory changes, all derived from expressions of potential functions that define their interactions. So there are additional model objects in TissueForge for writing explicit forces. So instead of describing a potential, you can just declare a vector that acts on individual particles between potentials and forces in the actual APIs. TissueForge provides the ability to specify these objects through like actual programmatic, like Python objects. So when defining a potential, you're actually creating something like an object that has properties and attributes that define model parameters and whatever else. And then you can use those objects to tell TissueForge, apply this potential to this pair of particle types or, this particular set. And there's a lot of flexibility in terms of being able to generate custom potentials. There's a pretty extensive library of predefined potentials and forces, but you're not limited to just using what, say, I thought of a year ago and happened to program in. You can define your own potentials and use them as if they had come along with the TissueForge package. As I said previously, there's support for solid, fluid, and electrodynamic modeling. And here's a good example of doing fluid dynamics in TissueForge using a particle-based formalism. In this sense, a TissueForge simulation will treat a fluid as consisting of a number of fluid particles. So these particles represent something like a parcel of fluid. And then there's a whole well-developed theory on what is the particle-based equivalent to fluid dynamics. This is called dissipative particle dynamics, if you're interested in these details. And the long and short of it is that it's possible to treat particles like fluids and do a simulation like what you see here, which is a particle-based simulation of a classic heat transfer problem. So in this case, this is looking at a cross-section of a fluid that's moving from left to right. And it starts with some initial temperature, which is shown here as a particular color. And then in the middle, there's a particle that's fixed in place. and has a much lower temperature. And you notice as the fluid flows by, the heat is transferring from the fluid into the fixed particle in the middle. There are a lot of details and theory behind this. This is all described in the TissueForge manuscript, at least at a high level. And if you're interested in these things, I am as well, and share that interest with you. So feel free to reach out, to get more into the details of how this is done, either theoretically or numerically. Now, it's at the point now where we can actually dive in and actually start building a simulation together. And the demo that I've prepared is a cell sorting simulation, which to me seemed most appropriate for being a breakout session in a CompuCell workshop. If we can get all the way to the end together, or if you follow through the slides on your own time, what you should find is that by the end of it, you can create a small cell sorting simulation in 3D, all using particles for two particle types. And so let's just get started. So again, here are the links. These are again in the chat, and I will paste them back in case anyone didn't catch them when they were first dropped in. So there's all of links in paper, repository, and the main documentation as relevant to our discussion today. And so here's our jumping off point. Again, you do not have to do this with me to get something out of this, but you are welcome to do so. The coding, I would say, is non-trivial, but not anything more challenging than what you've accomplished so far today. On the condition that you can actually go through the process of installing TissueForge on your computer pretty much in real time. And I think that's probably the biggest challenge here. So if you don't even want to deal with the headache of getting the software onto your computer right now, again, feel free to just sit back and listen, ask questions, and you can do this on your own time with the slides after our session and the workshop today. If you want to try to trudge along with me, your starting point is whether you have Conda installed on your computer currently. If you do, then you can search and get the Anaconda prompt open on your computer. Or if you set it up beforehand like me, then you have it integrated directly into your command prompt or terminal. If you want to catch up and don't have Conda installed, this is the place where you need to start, and I would ask that you do so immediately and quickly. Question in the chat, does the mini Conda from CC3D work here? It does, but I don't recommend it on the risk of potentially compromising your CompuCell installation. It's a good question, and in theory, it should work fine, but I don't want to send you off on a task that will make the rest of the workshop more challenging for you. So if at all possible, I would recommend getting mini Conda installed on your computer if you don't have it already, and just go through the quick process of installing TissueForge in its own environment so that if something goes wrong or whatever else, it has no effect on the rest of your progress throughout the remainder of the workshop. So very quickly, you can just search mini Conda download in Google, follow this link, and choose the link according to your operating system and just follow through. We don't have time to really dive into this, so if you get stuck, I'm just going to ask that you be merciful and follow along in terms of listening and complete this on your own time thereafter. Although typically this procedure tends to be pretty routine. So wouldn't expect it to be some massive undertaking to accomplish this if you want to give it a try. Now, assuming that you have Conda available, you can open an Anaconda prompt, or if you have it integrated in your command prompt like I do, you'll want to open a command prompt and create a new environment. And you can do so with the command Conda create -n and then just some arbitrary name, something that you'll remember. So create a Conda environment with a name that you provide, and you'll install TissueForge directly into that environment. I have already done so. The environment that I created on my machine is called CC3D WS_TF, CC3D Workshop TissueForge. So if you want to follow along exactly as I've done it, then you'd first start with the command that I just put on my command prompt. If you can see that okay. I'll give it to you in the chat. Conda create -n and CC3D WS_TF. That should mostly do nothing. It'll ask you to confirm creating an environment. You can press Y to confirm. And then you can get TissueForge installed by first activating that environment. Conda activate CC3D WS_TF. If you use the same name as me, put that in the chat for you as well. If you followed up to that point using the same name as me, then you should find yourself looking at a modified version of the command prompt where you see the name of the environment here in parentheses on the left. That lets you know that you have the environment correctly activated. And then there's the installation command. It's shown here on the left-hand side of my screen. I'll give you the command in the chat for this one as well. So this is installing. If you're interested in the details of Conda, it's use the CondaForge and TissueForge channels, and you just want to install the TissueForge package. Everything in TissueForge for the Python API, actually for all three APIs, it's all available just through this one Conda package. So issue that command, it'll do some thinking and ask you to confirm. You can press Y to confirm. And by the end of it, what you should find is if you do something like type Conda list, give you a big list of software packages, and you'll find the TissueForge is listed. It may take a moment for Conda to complete solving the environment and installing it. That's okay. We can talk here through a couple of additional details while it works. Let me know if you're just absolutely dying to keep up and waiting on the installation, and we'll see if we can stall for a couple of seconds to give those who want to do this with me a chance to do so. So the command again is in the chat for those of you following along. And once you're at this step where you have the Conda environment activated and TissueForge installed, you are good to go for at least programming interactively in Python or in a Python script. And you can do a very quick test by first typing Python and then import tissue_forge as TF. It may do a little thinking the first time you issue this command, but then you should find that no errors are returned. The TissueForge package has everything that's needed to complete all of the exercises today. Anyway, so I'll say that the easiest, most straightforward way typically to develop a TissueForge in Python is to use a Jupyter Notebook. Similarly to how we worked yesterday in the CompuCell Python API. If you want to go this route, you can additionally install the packages to work with TissueForge in Jupyter. And I'll give you the command to also install these dependencies. So it's notebook, IPy widgets, and IPy events. Jupyter is not a dependency of TissueForge, but does have native support for it if TissueForge detects Jupyter has been installed during runtime. I'll say that there have been intermittent issues on some operating systems with Jupyter Notebook. And so just to play it safe, we are going to avoid Jupyter Notebook simulation for TissueForge, just to make sure no one gets left behind on erroneous errors that have been kind of popping up randomly. I'm going to use Jupyter Notebook to write some Python script. For those of you who maybe don't have an IDE like VS Code, already installed on your computer, and you don't have a straightforward way to develop a Python script, you can issue this second install. Oh, I'm sorry, I have a typo in that last command I gave you. Let me correct this before someone gets distracted on just a silly mistake of mine. There's a corrected version of that command there in the chat. So if you don't have an IDE installed, to where you're well set up to edit a Python script, you can use this command to install Jupyter Notebook. That's what I'm going to do. And we'll just do some basic Python scripting using the interface that Jupyter Notebook provides. So if you want to go that route, issue that second command, the corrected one, not the previous one that I put in. And then you can afterwards launch Jupyter Notebook, again with the Conda environment activated with just Jupyter Notebook. Second to think about it. And when you go to a web browser, should find that you end up somewhere similar to what you see on my screen. Now, again, you're not obligated to do your Python scripting this way. If you have a preferred IDE, if you like VS Code or PyCharm or comparable, there's no reason why you need to work in Jupyter Notebook any way that you would develop Python code. Otherwise, all functionality and rules apply for TissueForge. So again, don't feel obligated to go this route. This is just a really accessible, straightforward way to get everyone on the same page without any additional installation. So I'm going to jump back and forth. Actually, let me know if this is okay to go split screen on this, because what I'd like to do is sort of code along and talk through things simultaneously so we can issue some code, do some execution and see the effects. First, starting off with just launching a TissueForge simulation in general, so you can get a sense of what to expect here. So if you are working with me and following along, this is how we're going to do this. So in Jupyter Notebook, we are first going to create a Python script, not a notebook, unless you want to try and see if Notebook works on your installation. I can guarantee for all operating systems that a Python script will work at the moment. So if you want to avoid any hassle, just do a Python script like I'm about to do. You can create a new one in Jupyter Notebook by going to the top right of your screen, clicking New, and then New File. I'm going to name mine, say tf_demo.py. tf_demo.py. And then right click or just double click, go to Open. And you should find just an empty script like what you see on my screen. So again, you first, the top right part of the screen, click New File, and then if you're really following along closely with me, tf_demo.py, double click it, and that'll take you here. And we can do a first quick sanity check and see what a TissueForge simulation looks like at its most basic by first importing tissue_forge. That's the TissueForge Python package. We're gonna go a little lazy here and say import TissueForge as TF. TF is how we'll generally refer to the TissueForge Python library. And we'll do the two most basic procedures to get TissueForge to show up on your screen. First, we'll say tf.init, no arguments. We'll add one momentarily. This initializes TissueForge, makes it ready to do something. And then secondly, tf.show, no arguments. And this will make TissueForge pull up an interactive window. So if you're following along with me, just import TissueForge as TF, then tf.init, tf.show. Let's save. And then let's get set up to actually execute this and see what happens. So to execute this, if you're following along with me, we can go back to the navigation part of Jupyter. And again, in the top right, click New. Writing is quite small. Thank you for letting me know. See if that's better. Import TissueForge as TF, tf.init, tf.show. If you're executing this in the same way as me, then go back to navigation. Top right, click New, Terminal. New Terminal. Click that. You should have another tab pop up. It's like I had an error launching mine. Let me try that again. Interesting. Michael, have you ever seen that before?
I have not.
Let's try console. Give it just 1 second. Has anyone else see at least one other person is getting the same error? Yeah, this is not one I've seen before. Same error, 2 people getting that error. Okay. Let's see if we can solve this by just restarting. So I'm going to close my browser, and on Windows, I believe it's Control X or Control Z, one of the two. I think on Mac it's Command Z. Susan asks, is the Python module TissueForge somewhere? It's installed in the Conda environment if you completed that step. I'm going to try relaunching this and see if maybe that can resolve this for me and generally for everyone. So I closed my browser. Then
You can also try opening a different browser. It seems like when people get this issue, it's like a browser specific issue.
sure. All right. I essentially just completed all of our previous steps again. Conda environment activated and then issue the command Jupyter Notebook. Let's try again, going to the top right, click New, and then Terminal. Hopefully we have better luck. Katrine's on Visual Studio Code. That's probably a more reliable solution than what we're seeing here. Well, this one is actually really new to me. Unsure why this is happening. I apologize for the delay. Suppose probably the best way to do this, at least for now, you can try doing this with different browser. For those of you who have VS Code installed, you can code this up in VS Code. For me, at least, editing the Python script is available, and that's fine. There is a way that we can address or deal with this if you can bear with me. Open another terminal or command prompt. We'll see if we can fix this on the fly. Open another terminal or command prompt. First, activate the environment that TissueForge is installed into. You don't have to close the other one. Then navigate to wherever you've created this Python script. It would have been the working directory where you first launched Jupyter Notebook. For me, I was in see. You navigate to wherever this Python script was created. And then you can just type Python and the name of the file. So again, wherever this script was created, you can continue to edit it in Jupyter as follows, or if you're in VS Code, it's probably an easier solution at this point. Then open another command prompt or terminal, activate the Conda environment, navigate to wherever this Python script is, and then you can execute it by typing Python and then the name of the script .py. So if you're with me and you've written in your script something like what I've written in mine, when you issue this command, you should find, with any luck at this point, that you get an empty simulation domain. This is the TissueForge universe. Should be a yellow cube with a grid in the middle, and you should find that when you click and drag, you can rotate around. If you have a wheel on your mouse, or if you're using a trackpad and do something like a zoom operation, you can zoom in and out. You can do the same by holding Control and then clicking up or down. Sorry if you're prone to motion sickness, this will be over soon. There are also predefined views, so you can press like Shift F to look at the front, Shift T to look at the top. You can reset the view by pressing R. And you also have the ability to pause and resume the simulation with your spacebar. So it begins as paused. You can't tell when it starts running because nothing is in here, but once we actually get some objects into our simulation, you'll find that you can pause and resume the simulation with the spacebar, and you can browse around as the simulation is executing or when it's paused. So if you followed along and kept up with me to this point, you should have a TissueForge universe that you can roll around with your mouse. All right, you can close this and the terminal will just return. And what we can do, for those of you who are working with me, we can do some edits in our Python script and then just come back to our command prompt or terminal and just issue the command again, and we'll see the updates when we re-execute. All right, so let's speed along so we can actually get to at least a little bit of some content that's potentially thought-provoking. Just naively, we're going to add to this call to init. We're going to specify a cutoff. Cutoff equals 3. This is what's called a cutoff distance, and this tells TissueForge the maximum distance over which two particles can interact. The details for now are mostly unimportant. We're just going to add this just for the sake of the exercise, and noting that there are a lot of options that can be used to particularize how a simulation executes, all just through the init command. So tf.init with cutoff equals 3. Now, let's continue. And as discussed, TissueForge has a type-based specification. So let's define some particle types. So we're going to do a cell sorting simulation, or at least get the start of on building one. And to do so, we're going to define 2 particle types. And in general, in TissueForge, in Python, there's an analogous way to do this in C++. We define particle types using Python classes. And you can see an example of our accomplished step here on the left. So to define a new particle type in TissueForge 1 first, defines a class using the keyword class, and then just a name that you want to give to your type. We're going to define types A and B. Those will be the 2 types for cell sorting. And so here I'm going to define my definition for my A type, just using the name A type. Class A type. This will be the definition of the first particle type. And TissueForge provides a class that you can inherit from that will assign all of the model like type specification features that come with default values, and you can particularize to your liking as relevant to your application. You can do so by adding parentheses after A type and then say tf.particle type spec. This is the standard template definition for a particle type. And we will build our particle types based on that template and customize features about it according to our liking. If you're getting, I see in the chat, getting errors, no module, TissueForge, make sure the Conda environment is activated, TissueForge is installed into it, and then when executing the Python script, you must have that Conda environment activated. So try that out, see if you have better results. So particularizing our type-based specification, there are all sorts of properties defined on these classes. They all have default values, and then you can customize them however you want. So for example, we can say that particles of our A type have a mass of 40. We can say that they have a radius of 0.4. Defaults here are 1 and 1. And as discussed previously, we can also customize what dynamics particles of this type have. The default is Newtonian, and in this case, we're doing multicellular modeling, so we'll say the dynamics are overdamped, tf.overdamped. I see Katrine verified that the Conda environment was activated and got the same result. Same, try issuing the command Conda list and verify that TissueForge is in the installed package list. Henry, I have not seen that issue before. Symbol not found, CRC32. Let's connect after this and let me get some details about that, because this may be just an issue with the builds that I've not had reported to me yet. Okay, so we particularize the dynamics for this type to be overdamped instead of Newtonian. And the very last thing, this one's also totally optional. We're going to particularize the way that particles of this type are visualized. And there are a lot of predefined features for how to do this based on real-time simulation data. You can show things like an updated representation of each particle's speed or forces acting on it. In this case, we're going to just make our particles of A type red. You can do that by setting the attribute style to a dictionary where the key is color and the value is red. That's it. Now, while we're at it, let's go ahead and add a second cell type. In this case, we'll call it B type. And we're gonna use some Pythonic features here and just say that our B type cells are identical to our A type cells by saying B type and then parentheses A type. If you don't know what that means, this is inheritance. It says that B type starts by being defined in the same way as A type, just like we use the template particle type spec to define our A type. And then everything that we specify after that is some customization of everything that's inherited from A type. And in this case, the only thing we actually want to change about our B type is to make it look different. Particles of these two types will be identical in that they'll have the same mass, the same radius, same dynamics, same everything that is applied by default that we've not particularized. The only difference, well, one is that particles of B type will be of B type and not of A type, which in the specification has real meaning. And secondly, they'll look different, so we can clearly identify them in simulation. Now, the next important thing is that this is just a declarative specification that really actually does nothing in TissueForge per se. This is, excuse me, this is a specification that TissueForge knows what to do with. So here, this doesn't actually execute anything in the TissueForge backend. Instead, we can use these class definitions to make TissueForge create a particle type by using the command get. So each of these particle types has a method get, takes no arguments. And when you issue this command, it will tell TissueForge create a particle type based on everything I've defined and everything that's default defined otherwise, and give me that object. Give me a reference to the type that was created. That's what's done here. Create a particle type based on my type specification, and then give me a reference to the type that was created. And we want a reference to the type that was created because we can use it to create particles. When we use a particular particle type to create particles, particles of that type will be created. That's the idea. So let's do this also with our B type. So B equals B type dot get. So now TissueForge will have created a type for A type and for B type. And we're getting those particle types and assigning them to A and B. If you're with me, we're going to move on to the next part. And I think actually before we do that, let's just do a quick test. Just to actually see something show up in simulation. So before we proceed, just as a very quick sanity check, sort of naively just add the two following commands. Say a.factory 100, b.factory 100. So in each of those particle types, call factory and just enter 100, or you can do 1,000 if you want. But just add those, save, and let's switch over to our command prompt or terminal. Yes, request for code so far in the chat. Great idea. Here's what I have so far in the chat. And now up to this point, let's go back over to command prompt or terminal. Again, with the Conda environment activated and presuming that TissueForge is installed into it. Do Python and then the name of the Python script. And enter. And if no errors occur, you should find that now we have, at least in my case, 100 red particles and 100 blue particles. These are particles of A and B type, styled as specified. Now, as I mentioned earlier, you can pause and resume a simulation by pressing the space bar, and you may try that out and press the space bar and notice that it doesn't look like anything happened. And that's because nothing is happening. In this case, we've created particle types and we've created particles of those types. But one thing we've not given to the simulation yet is any description of how these particles interact with each other. So there are particles of particular types, but no instructions on how they are to interact with each other. In our case, we're interested in doing self-sorting. So our next step then is to now tell TissueForge how these particles interact with each other on the basis of type. So you can close the window. If you want to follow along directly with me, I'm going to delete those two calls to factory. That was just a simple test. Hopefully, if you're following along, you got a similar result. You may notice every time you issue that command that the particles are placed in different locations. That is by design. So if you don't provide any information about where particles go, then they are placed into the simulation at random. You have all sorts of different ways to control the number of particles that are created and where they're placed, what are their initial velocities. But just in the very least, if you ask for a particle, TissueForge will give you a particle and put it somewhere. All right, moving on. So I mentioned earlier that there are potentials and there are forces and lots of ways that you can specify how particles interact with each other, specifically through potential or explicit force representations, and that this is all done by creating objects that represent those different potential or force model specifications. We're going to work with a couple of potentials here. In particular, we're going to use the potential function that's shown here. This is the Morse potential. And if this equation doesn't mean anything to you, that's totally fine. Suffice it to say that this is a really simple way to describe something like adhesion and volume exclusion between two particles that are near each other. And also suffice it to say that when choosing our parameters appropriately, we can actually generate something like differential adhesion when applying this potential to particles of different types, where the parameters are chosen according to the pairs of types. So very similarly to how cell sorting is done in CompuCell, where you choose contact energy values, and if you choose them in a clever way, you end up with an aggregate that will segregate by cell type. We can do something very similar here, just by choosing one difference in parameter in the Morse potential based on the two types of particles for which we define an interaction. So let's just do it. Let's try this. So in general, the way to create a potential in TissueForge is with tf.potential. And if you'd like to use one of the many predefined potential functions that are provided in TissueForge, there's Coulomb forces, there's harmonic potentials, all sorts of different commonly used potential functions. In this case, this is predefined and provided in TissueForge under the name Morse. So tf.potential.morse. Calling this and providing parameters will create a potential object and return it to you. And then you can later tell TissueForge which types of particles you want to apply this potential to. So let's just follow the procedure that's shown here on the left. So we're going to create three potentials, and this corresponds to the different combinations of our two particle types. I'm going to define a potential for interactions between A and A type particles, B and B type particles, and A and B type particles. And we're going to name these appropriately. So pot for potential and underscore AA would be the potential for particles of type A and type A. And naively, we'll follow along on the instructions here and specify the model parameters that are shown in the equation. First, for A and A type particles, we'll say that D equals 3, A equals 5, and then define some somewhat in the weeds details on the distances over which these particles can interact, and they can interact over relative distances of between -8 and 2. This just tells TissueForge that particles of relative distances as measured from the contact distance of their radii, over what ranges of relative distances can particles interact through this potential. And we can copy this first entry to quickly generate the other two. So our second one will be pot_BB for B and B type particles. And we're going to say that those parameters are the exact same as for our A and A type potential interactions. And then lastly, we will create particle potentials for A and B type particle interactions. And in this case, the only difference will be that our D parameter, the first one, will be reduced by an order of magnitude. So D equals 0.3. Otherwise, everything is the exact same. So our homotypic interactions are identical, but our heterotypic interactions have one parametric difference. And then generally can use in TissueForge what is called binding, which is to take an object that describes some interaction and apply it to objects of some, say, category. In this case, we're going to apply our potentials to particles on the basis of type. And we do so with tf.bind.types. What this tells TissueForge, tf.bind.types, it says, take this potential that I'm giving you and then apply it to all particles of the two types that I specify thereafter. So our pot_AA will be applied to interactions for particles between particles of types A and A. And maybe you guessed it, we'll also bind pot_BB to particle types B and B, and tf.bind.types pot_AB to A and B. I'll give you an updated version in the chat based on what you see on my screen. If I have typos, then at least you'll have the same ones as me and we can debug in the same way at the same time. And if you're with me and you want to test this out again very quickly, you can add a couple of prototype lines before show. And again, say use a.factory. In this case, we can maybe fill up the space a little bit more, say a.factory and say create 1,000 particles, b.factory, create another 1,000 particles. This is just a bit of simple test code. And then switch back over to command prompt or terminal, Python, and then if you're following along very closely with me, tf_demo.py. Issue that command. And if you, like me, are testing with 2,000 total particles, you should find a much more crowded universe. And in this case, you should also find that when you press the space bar, now you get some motion. I'm actually going to maximize a little bit more visible. You should find that you see particles of the same types are beginning to aggregate. Now recall, there were no differences in the potentials that were applied to particle interactions of the same types. We said that pot AA and pot BB were identical in parameters, and then we applied those to particle interactions between either A and A types or B and B types, whereas our pot AB had just that one difference in a parameter, where we reduced the D parameter by a factor of 10. And excuse me, the effect is evident here in that the tendency to aggregate between particles of A and B types is much weaker than the tendency to aggregate by the same type. And that is a particle-based representation of cell sorting. This is differential adhesion in a particle-based formalism. Everything in this session from here on out is bells and whistles at this point. But it is we've accomplished enough to be able to say that you have now officially built your first TissueForge simulation. So congratulations if you followed along. If you're watching this video in the future and you're following along, then congratulations from me in the past. And so I think we have what, 15 more minutes, Michael, is that correct?
Yes.
Great. Okay, so we can blast through, a little bit more to get a sense of some more things that you can do. I mean, the whole point here for the most part is to give you a working familiarity of some of the things that you can do with this software, and then get your hands dirty a little bit with actually doing a bit of coding with it. So whatever we can accomplish from here on out is just icing on the cake, as they say here in the States. And so we'll see what else we can get done here. So we go back to the code, you can close the window, you can erase, I think you can keep the prototype code with the factory call, that's fine. More importantly, I want to do a little bit more work with creating forces. Question in the chat, do you do self-packing or like bubbles or foams? We don't have anything planned for today that's specifically to that effect. I have seen work to that effect more with algorithms that are more similar to cellular POTS model. Yeah, this is one of James Glazer's big like early research fields is on bubbles and foams. There's nothing in TissueForge that's really specific to bubbles and foams per se. That's for sure. Maybe there's an equivalent form using vertex modeling, though I'm not aware of anything like that. The TissueForge does have a whole vertex modeling module that maybe would be relevant to foams. This is honestly not really my domain. Michael or anyone else, feel free to chime in if you're aware of using these methods in those domains. Okay, in the meantime, so we've created potentials. Again, there are all sorts of built-in potentials besides the Morse, Coulomb, and harmonic. Potentials are some obvious examples. And again, you can also create your own potentials for, say, applications where you're interested in something that none of us thought of to provide. So you're not limited to just the things that are distributed as built-in features. But additionally, you can also create explicit forces, which is just a vector-based representation of adding a process into a simulation. You can also bind these to types, and we're going to use one of the built-in force definitions that's provided in TissueForge. And in this case, we're going to add some noise. So we're going to make our particles move around with some randomness. This is a model of intrinsic cell motility, which for those of you into more of developmental processes or whatnot, this is a particularly important feature for making cell sorting possible. Not going to digress down that rabbit hole, but that's an interesting feature of cell sorting. When doing these kinds of simulations, we're just going to add some noise to our particles, and we can do so similarly to creating potentials. So we can create a force with tf.force, and then one of a number of methods to create built-in force instances. In this case, for a random force, we can just use tf.force.random. And we provide information on the mean magnitude of the force and the standard deviation of the magnitude. In this case, we'll say that our random force has a mean of 0 and standard deviation of 50. The direction of that force is randomly chosen for you by TissueForge and is updated as the simulation progresses. And in this case, the force that's created is returned. And so we're going to say R force, or random force, equals tf.force.random, mean of 50, standard deviation, or mean of 0, excuse me, standard deviation of 50. And we can do some binding, which again is to tell TissueForge, given some particular process, apply it to corresponding types. And in this case, we can bind forces to particles of a particular type. And in this case, we'll say apply our random force to all particles of type A, tf.bind.force, pass R force, tell TissueForge apply R force to all particles of type A. And then likewise, we can do the same to apply our random force also to particles of type B. Give you an updated version of the script in the chat. This again has my prototype code that just randomly adds 1,000 particles of each type. So if you want to catch up or just do a sanity check, there's an updated version of the code. I'm going to go back to the command prompt and try it out. Back here, somewhat crowded simulation domain, starts out paused, press spacebar to resume. Now you should find that you have some noisy particles. You should still see the sorting effect, but now with some noise. Again, you can press pause or press the space bar to pause and still navigate around. If you really want to dive into some details, you can move around, resume. And again, you can reset the view with R on your keyboard. Question in the chat, what would be a good use for TissueForge? Yeah, so that's a loaded question. And the 30-second answer is that the intended scope of TissueForge is molecular dynamics to multicellular modeling. I will provide links again. Actually, I can do that right now. The new paper on TissueForge and PLOSComp Bio shows demonstrations of example use cases at just about all of those levels, or at least enough to give you a sense of how TissueForge can be used to do modeling at relevant scales between molecules to multicellular tissue. And then there are lots of ways that TissueForge is being used otherwise to do interesting things that are not described in that paper. If you really want to know more, email me and we can talk separately in more detail. Okay, we have just a couple more minutes left. I think that probably this is just a good point to break for now. Everything that's designed here from this point on, as I said a few minutes ago, this is mostly just bells and whistles from this point on. And the content that is prepared here is really intended to get you into something like a working familiarity for the ways that you can set up your own interactivity with TissueForge. Whether it's creating more custom like keyboard callbacks. Right now TissueForge is distributed where you can pause and resume a simulation by pressing your spacebar, what if, say you wanted to create more particles every time you press, say, the plus key on your keyboard, or say increase the noise or decrease the noise of particles and observe the effect on cell sorting. There are ways to add additional keyboard callbacks to make changes to your simulation. These slides will be shared, and there is material here that's been prepared to walk you through that process of continuing to develop the simulation that we've already started for adding those kinds of features. I don't want to push it late and make everyone fall behind on the rest of the day. So I think that this is actually a good place to stop for now. So we have a few minutes. Maybe we can open it up for any questions or discussion with the few minutes that we have left. Is that okay, Michael?
Yep, that's a great idea. That's what I was going to suggest exactly.
Great.
If anyone has any questions, either you can unmute or ask, or you can just ask directly. I'll parrot a question that was asked in the chat. Asking, can you do an event-based conditional where you'll have a something similar to a phenotype change?
Yeah, it's a great question. So there is full support for changing the type of individual particles. And the interface is really straightforward for walking through the procedure of telling TissueForge, this particular particle that I'm interested in, make it a different type. And it's certainly possible to make those changes on the fly during simulation, whether it's in some conditional that you pre-program as an event, and I think actually the later parts of the walkthrough that's prepared, yeah, if you watch this animation, you can see it. This walkthrough will actually take you through the process of setting up a keyboard callback where you change the type of particles using keyboard callbacks. So yeah, you can create particles, destroy them, modify them, and even change their type at any point in simulation after they've been created, including in real time in response to events that you pre-program. It's a great question. Any other questions, or we have just a couple of minutes left. It's okay to just be done early. But a few more minutes of time where we can unpack anything else that was maybe of interest or maybe unclear. Vertex modeling, is it in 3D? That's a great question. It's best developed for 2D currently. Yes, it is in 3D. There are aspects of the 3D form that, let's say, could use improvement. Not so much in terms of the supported functionality per se. You can, just like with working with particles, you can create vertex model cells, you can modify them, you can divide them, change properties about them in real time, and you can do so, in either 2D or 3D. As we were developing the vertex model formalism for TissueForge, we found that there were some real limitations in some of the topological dynamics in 3D, where an operation like dividing a cell or say penetration of one cell through the interface of two other cells. In 2D, the topological dynamics, the mathematical theory there is pretty well defined, and there's not a lot of ambiguity. But there were just some aspects of those details that when you go to 3D, that theory hasn't been as well defined. So we stopped at the point of having the same support that's in 2D as in 3D, with the expectation that over time we have some actual theoretical mathematics to do to make the 3D vertex model formalism more robust? That's a great question. Tensegrity models. That sounds intriguing and also foreign to me.
Yeah, tensegrities are a tensional model of a solid object. Like they're not exactly solid. They're more of a lattice, but you can describe the cell cytoskeleton
Hmm.
using tensegrities. And cells are in tension, so they are an object that is in tension.
Mhm.
And they behave differently than a normal building, we'll say, just a normal truss, because if you've got an object in tension and you change the force on one part of it, it will change the whole object slightly.
Mhm.
So you go at this with finite element analysis, and it's an incremental force that they apply, a tiny little incremental force that they apply to get where they're going with their model. And every time you hit it with an incremental force, it kind of changes the whole shape of the object.
Mhm.
So it gets out of control in a hurry. And so I've discovered that if you just take the first iteration, like it tries to iterate off into infinity. If you just
Oh,
take
yeah.
the first measurement, that helps. It just but you get J curves with tensegrities quite often if you've got them stretched in the right direction. And they also have soft modes where they collapse. So they're interesting. And the mathematics is somewhat complicated. I don't
Sure.
think they have it figured out. And it, like I said, the finite element analysis doesn't quite fit.
Yeah. I mean, in a somewhat naive sense, I mean, just based on what you've described, this sounds like the vertex model support in TissueForge could be of interest to you, at least at the level of trying it out. Again, there are
Okay.
some limitations in the topological dynamics in 3D that just need better theoretical mathematics behind it. But these kinds of operations of having like active cellular forces that have real effects on the overall morphology of a tissue. I mean, this is well within the domain of what TissueForge supports in the vertex modeling.
Okay, well, I'll have a look at the vertex modeling. I need some sort of verification method, because I've got this going in ComSol. You could do it in ANSYS or whatever, but then I would like a different model, and your 2D model looks like it would be great. And see if I could get some stress strain curves. That's kind of what I'm working from. Very straightforward stress strain curves. See if I could find something that matches. I know the data from atomic force microscopy kind of matches what I'm doing, but yeah, I need some verification for my
Okay.
models.